In this video, we're going to conduct a hypothesis test regarding the difference of two means when we have independent samples. Now, this is different from the scenario in the previous videos where we had dependent samples. So let's start by looking at the sampling distribution. So the sampling distribution of the difference of two means when we have independent samples with population standard deviations unknown, and this is called Welch's T. Suppose that a simple random sample of size n1 is taken from a population with unknown mean mu1 and unknown standard deviation sigma1. In addition, a simple random sample of size n2 is taken from a second population with unknown mean mu2 and unknown standard deviation sigma2. If the two populations are normally distributed, or the sample sizes are sufficiently large, meaning n1 is greater than or equal to 30 and n2 is greater than or equal to 30, then T equals the quantity x bar 1 minus x bar 2 in quantity minus the quantity mu sub 1 minus mu sub 2 in quantity all over the square root of s sub 1 squared divided by n sub 1 plus s sub 2 squared divided by n sub 2 approximately follows student's T distribution with the smaller of n sub 1 minus 1 or n sub 2 minus 1 degrees of freedom, where x bar sub 1 is the sample mean and s sub 1 is the sample standard deviation from population 1, and x bar sub 2 is the sample mean and s sub 2 is the sample standard deviation from population 2. So, in a nutshell, what we're saying is that these distributions follow a student's T distribution with the smaller of n sub 1 minus 1 or n sub 2 minus 1 degrees of freedom. Now, to be totally honest, that's a little bit conservative, and we'll talk about that degrees of freedom scenario a little bit later on. But let's look at our process for conducting a hypothesis test. This process is very similar to the process that we've seen before. The only difference is the details. So testing hypotheses regarding the difference of two means, and again we are talking in this particular case about independent samples. To test hypotheses regarding two population means, mu sub 1 and mu sub 2, with unknown population standard deviations, we can use the following steps provided that the samples are obtained using simple random sampling or through a completely randomized experiment with two levels of treatment. So again, we need randomness. The samples are independent. So the individuals in sample 1 do not have any relation to the individuals in sample 2. This is not a matched pairs scenario. The populations from which the samples are drawn are normally distributed, or the sample sizes are large, meaning both sample sizes have to be 30 or more. So if our sample sizes are less than 30, we will have to do normal probability plots to ensure that those data come from a normal distribution. We'll also have to make sure there are no outliers. For each sample, the sample size is no more than 5% of the population size. So again, the purpose of that is to ensure that the individuals in each sample are independent from each other. So again, there's two types of independence. In this case, there's independence between the two samples. That's what the second bullet's indicating. And the last bullet is there's independence within the sample. So the individuals in each sample are not related to each other, and the individuals within each sample are not related to the individuals in the other sample. So again, that's the distinction between bullet 4 and bullet 2. So as long as we meet those conditions, we're going to be able to conduct our hypothesis test. And other than the specific details of how we calculate the test statistic and the degrees of freedom, this hypothesis test is going to work pretty much like the other hypothesis tests that we've done so far. So step 1, determine the null and alternative hypotheses. The hypotheses are structured in one of three ways. So the null hypothesis is that mu1 equals mu2, and then the alternative hypothesis will be that mu1 does not equal mu2. That'll lead to a two-tailed test. Mu1 is less than mu2. That'll lead to a left-tailed test. Or mu1 is greater than mu2. That leads to a right-tailed test. And just like we looked at when we were dealing with proportions, this may also be structured as mu1 minus mu2 equals 0 versus mu1 minus mu2 is not equal to 0. So it may take that form, and this is how we'll see it in StatCrunch. And likewise, this might be mu1 minus mu2 is less than 0. That's equivalent. And this might be mu1 minus mu2 is greater than 0. That's equivalent. So our textbook looks at it this way, but when we look at StatCrunch, it'll be mu1 minus mu2 equals 0 versus not equals to, less than, or greater than 0. Step 2, we'll select a level of significance alpha depending on the seriousness of making a type 1 error. Step 3, whether we're using the classical approach or the p-value approach, we're going to compute the test statistic. Now, the way we calculate the test statistic, that's what makes this test different from the other hypothesis tests. Otherwise, it's pretty much the same. You will notice that all of the hypothesis tests work pretty much the same way. They have the same structure. The difference is just in the details of which model we're using. So, T naught is equal to the quantity x bar 1 minus x bar 2 in quantity minus the quantity mu1 minus mu2 in quantity, divided by the square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. So again, whether we're using the classical approach or the p-value approach, we're going to calculate that test statistic. Now, this is going to follow a student's t-distribution as a general rule. Again, if we know the population's normal exactly, then this will exactly follow a student's t-distribution. If we have a sample size of 30 or more, but not an exact normal distribution, then this will approximately follow a student's t-distribution. Now, we're going to use table 7 or some other means to determine the critical value using the smaller of n sub 1 minus 1 or n sub 2 minus 1 degrees of freedom. Now, oftentimes the two sample sizes will be the same, so these will both have the same value. But if the size of sample 1 is, say, 30 and the size of sample 2 is 20, we're going to use the smaller degrees of freedom. Now, so again, if we're using the classical approach, next we're going to determine our critical values. So we're going to use the t-distribution to do that. Again, using the appropriate degrees of freedom, and that's the smaller of n sub 1 minus 1 or n sub 2 minus 1. So again, if we're doing a two-tailed test, we'll split alpha between the two tails and determine the two critical values. If we're doing a left-tailed test, then alpha will be in the left tail. We'll figure out that critical value. It'll be negative. And if we're doing a right-tailed test, then alpha will be the area here in the right tail, and we'll figure out that critical value. Step 4, we'll compare the critical value to the test statistic. Or again, I prefer to say we compare the test statistic to the critical value, and it works the same that we've seen before. If the test statistic falls either in the left tail or the right tail of a two-tailed test, then we will reject the null hypothesis. If it falls in between, we will not reject. If it's a left-tailed test, if the test statistic falls to the left of the critical value, we'll reject the null hypothesis. Otherwise, we won't. If it's a right-tailed test, if the test statistic falls to the right of the critical value, we'll reject the null hypothesis. Otherwise, we won't. And so once we decide that, we'll state our conclusion. Now, if we do the p-value approach, using the p-value approach, we're going to calculate the test statistic, and then we're going to use that to figure out our p-value. So if we're doing a left-tailed test, the p-value will be the area to the left of the test statistic. If we're doing a right-tailed test, the p-value will be the area to the right of the test statistic. If we're doing a two-tailed test, the test statistic will either be negative or positive, so we will find it and its opposite, so that we'll have one negative value, one positive value. And the p-value will be the total area on the outside of those two critical values, so the total area in the two tails. And again, that p-value will be double in a two-tailed test what it would be if it was a one-tailed test. Now we can also use technology to calculate our p-value. regardless of how we determine the p-value. If the p-value is less than alpha, we reject the null hypothesis. If the p-value is greater than or equal to alpha, we do not reject the null hypothesis. So again, all of this is the exact same as the other hypothesis tests we've been doing. The difference is the model that we're using and how we calculate the test statistic. Step 5, we're going to state our conclusion. So at this point, we're ready to look at an example, and we'll do that on a separate video.